I want to try to use this process to see if I can design um, a PNP amplifier. So let's start out with the same exact problem. And so we've got here, I'm going to clear my MATLAB script here, or my MATLAB command window. Okay, and so the few things that I have is I see that I have an input impedance of, or sorry, an output impedance. So Z out is equal to 33,000. I've got a voltage gain, AV is equal to 7. I've got a voltage source is equal to 25. It doesn't say it here, but I know that I have a beta is equal to 100. Okay, and so the first thing this tells me to do is that to set RC to match Z out. So I'm just going to do that. RC is equal to Z out. Great. And then it tells me to set VC equal to VS over 2. So I'm going to do that too. Okay, and now I need to calculate IC. So let's do a little calculation to make sure we know what we're doing. I know that I have to think about what my circuit looks like. So I've got a PNP circuit. So let's just draw that. I'm going to be going this way. So this, that's my VB. I'm going to have a biasing network, resistor network to give me my base voltage. And then I'm going to have a time varying signal on the input that I'm going to add to my base voltage. This is PNP. This is going to be my RE, right? Because this is my emitter. This is my collector. This is my base. This is going to be my RC. This is R1. And this is R2. And this is my VS. So I already know my VC. So I'm just going to write that. VC is equal to VS over 2. And that's going to equal 12.5 because my VS is 25. And remember, I'm doing that because my output's going to be right here, and I want to be able to have my output signal swing the full range. So that means I can start at 12.5, and my amplitude can go plus 12.5 and then down to 0, and I won't clip my I won't have a clipped signal. Okay, so what's next? Well, I'm calculating IC. That's right. So if I want to calculate IC, I know my VC value right here. So I know my VC is 12.5. I know my I know my RC because I already set it. And so I'm going to calculate IC. So IC is equal to VC over RC. And so that's going to equal 12.5 over 33K. So let's type that. And we get IC is equal to VC divided by RC. We get 3.8 e to the 4 amps, or 3.38 milliamps. And that's a C. All right, so let's see what's next. I think the next thing is we're going to set right here, we're going to set IE equal to IC. So IE is equal to IC. And then we're going to calculate RE from our equation. And this is actually AV is equal to a negative RC over RE, but I don't need the negative to calculate the values. So I'm just going to take the magnitude. So I know AV is equal to RC over RE. So rewriting it, I get RE is equal to RC over AV. I know AV is 7, and I know RC is 33K divided by 7. So if I type that in, I get RE is equal to RC divided by AV. I get 4.7, so RE is equal to 4714, yeah, ohms. So 4.7K. That's E. Okay, so now I know RE. So by knowing RE, I can calculate VE. And why is that? Well, that's because I know IE. So I have this value and I have this value. And so I'm just going to put it over here. So I'm going to say then my VE, so VE is the voltage here, right here. And so what I need to do is I can calculate the voltage drop across this resistor. So across RE by taking I times RE. And then if I subtract that voltage drop from VS, that's going to give me this VE value right here. So VE is going to equal VS, the voltage source, minus IERE. And so that's going to be 25 minus 3.8 times 10 to the minus 4, and then times 4714. Okay, and I'm just going to do that in MATLAB. So VE is equal to VS minus IE times RE. And I didn't get IE. Right, okay, so I need to set IE is equal to IC, and then I can run it again. So I'm just pushing up arrow, I go up to the past equation, and I get 23 volts. So VE is 23 volts. That's pretty high, so that's pretty close to the value of VS, right? So I haven't dropped a whole lot of voltage there. And let's just make sure that looks about right. Yeah, I think that's right. Okay, so next we're going to say VB is equal to VE minus 0.6, right? I drop 0.6 volts when I go from VE here to VB here. Okay, and so I'm going to write that in here. So I have it. VB is equal to VE minus 0.6. So I get VB is equal to 22.6 volts. Okay, so far I have RE and RC. That's great. And so by having my VB, I can now start working on my resistor network. So if I look here, I can also calculate my Z in right there, so I'll do that in just a minute. And now I can choose R1 and R2. And the first thing I want to do is I want to limit the current on the base by setting my R2 resistor much smaller than my Z in. So that way, most of the current will go to R2 here. Most of the current will go this way. So as my current comes down from my source through R1, it's going to split, and some is going to go to the base and some is going to go through R2. I don't want a lot of current going through to the base. So if I set the resistor value smaller for R2, then the impedance of my transistor, input impedance of my transistor, then I'm going to limit that current. So let's first figure out my input impedance is beta times RE. So Z in is equal to beta times RE. And so that's equal to 100 times my RE. So let's just do this. Z in is equal to beta times RE. And we get Z in is equal to 471. So yeah. So 471K for Z in. And now to find R2, here we can say R2 is equal to 1/10 of Z in. So Z in over 10. And so that means R2 is going to be equal to 47,000. 47K. Okay, and we can figure out now, we know, we can calculate I2, because if we know what the resistance is for R2 and we know what VB is here, then we know that the voltage drop across here is VB, and so we can calculate the current. So then I2 is going to be VB over R2. And so we have I2 is equal to VB divided by R2. Right, so we forgot. R2 is equal to Z in divided by 10. Now I can run that again just by doing up arrow, and I get I2 is equal to 0.48 milliamps. So I can also calculate IB. So IB is equal to beta times IC. So I'll type that in here. So IB, or IB divided by, whoops, I misspoke there. So let's just back up. IC divided by beta. Okay, so IB is equal to IC divided by beta. Yeah, so that makes sense. IB is 3.8 microamps. And now I can find I1. So remember, I1 is the current that goes from the source through I1. So from the source through I1 and then splits in IB and I2. So I can just find that by saying I1 is equal to IB plus I2. So I1 is equal to I2 plus IB. And I get I1 is equal to 0.48 milliamps. And now, finally, since I know I1, I can calculate the resistor value here, R1, because I know the supply voltage, I know I1, I know VB, so I can find the voltage drop across R1 is VS minus VB, and then if I divide by the current, that'll give me R1. So R1 is equal to VS minus VB over I1. Okay, and so I get R1 is equal to VS minus VB divided by I1. Okay, and so my R1 is 4.9 kiloohms. Okay, and that makes sense, right? So my R2 is 47K and my R1 is 4.9K. So that's 10 times as big, and I should be dropping a pretty small amount of voltage across R1 because VB is pretty big. So far I've got all of my resistors, so that's great. The maximum, so I'm going to have the same thing here, that I'm going to have my input signal that looks like this. And I want to know how big this amplitude can be. That's what I don't know. What voltage do I have there? Well, I can figure out V in, because that's just, I can get that from AV. So AV is V out over V in. So V in is V in, out over AV. And I know that's going to be 12.5 divided by 7. So I'm going to have 12.5 divided by 7. So 1.78. So V in, the biggest it can be is 1.78 to have the full swing in the output signal. And then last thing, I'm going to do the load line. And so remember here, this is going to be VEC now, because E is on the top, and this is going to be IC in milliamps. And my VCE I know is going to be at 25 because that's the max. So for cutoff, right, I'm going to have this. This is my E, this is my C. So I know that this is VS. So I know I have to have E is equal to VS, and I know C is going to be 0. So VS minus 0 is VS, which is 25. And so this is cutoff. And then saturation, I'm going to have, this is E, this is C. Now I'm going to have a wire connecting. So IC is going to equal VS over RE plus RC. So when I calculate that, I'm going to get IC sat equal to VS divided by RE plus RC. And I'm going to get that's equal to, so IC is equal to 0.66 milliamps. Draw that in here. So let's just say 0.66. Draw my line. All right, I look at where I'm actually operating. Is, where's my V? So if VE is 23.2, so let's see, VEC equal to VE minus VC. I get 10.7. So I'm going to be operating kind of sort of close to halfway. And then IC, I can just type IC here, and I don't have to look for it. It's 0.37, so almost 0.4. So I'm going to be like, let's see, does that make sense? So I'm probably a little over here a little bit. So, oops, if I can draw that back in, something like that. And maybe I'm like here, so that looks like about 10.7, and that looks about 0.37, so 10.7. And then this would be my IB curve, and my IB is, I can type that out to double check. It is 3.7, so make it 4 e to the negative 6 amps. All right, and that's it.